Let us now apply the concept of linear equations in this new manufacturing technique called additive manufacturing, or as commonly known, 3D printing. The way that this manufacturing technique works, at least with polymers, or one of the procedures for polymers, is that the polymer is heated and then is pushed through a nozzle that is circular in diameter. And as the material, which is at the viscous state, is pushed through the nozzle, there is a device that is translating the nozzle in a predetermined pattern in order to lay down the material that comes out of the nozzle and slowly build layer by layer an object of interest. So the material that comes out of the nozzle is cylindrical in cross-section. We can think of it as strands of cylindrical spaghetti that we lay next to each other at predetermined lengths in order to make one layer. Then we have another layer made up of another set of cylindrical spaghetti pieces, and so on and so forth, until we fabricate the whole object. So we are going to try to understand how to find the time that will be required, ideally, in order to fabricate a component of a desired volume. We are not going to be concerned with other features, just how long will it take to dispense or extrude and lay down this volume. So we are interested to find the time in order to fabricate an object of a known volume. And let us go ahead and assume that our object, just for the sake of discussion, is a cuboid with a desired volume VO, the object volume. In order to find this time, we need to know the linear length of all the little pieces of pasta that we need to lay. So if I sum up all the lengths of the pasta, it will be a total length L. These cylindrical pieces of pasta have a cross-sectional area A, and we also need to know the speed with which a device is laying down these pieces. So let us look at the analysis, put this statement into equations, and try to derive a linear equation that will relate the time with the volume as a function of the other parameters. The volume of the object will be equal to the linear length of the sum of all the cylinders times the area of the cylinders. The cylinders are all of the same area. So here we can evaluate the length as being 1 over A times the volume. And of course, if we carefully observe this equation and we assume that the volume is the independent parameter and the length the dependent parameter, we observe that the slope is 1 over A times then the independent parameter VO. So this is the equation of a line with a 0y-intercept. From motion analysis, if we were to have a motion device that will be manipulating the head that is dispensing these cylinders, the speed or velocity will be equal to the distance that we need to travel, L, divided by some time. And we can further manipulate this equation and say that the time is equal to 1 over speed times the length. Again, this is in the form of a linear equation with 1 over the velocity being the slope of our line, if L is the independent variable. However, we also know one expression for L, so we are going to substitute that expression. L is 1 over A times the volume of the object. So I'm going to rewrite this equation as time equals 1 over V times A times the volume of the object. This equation is in the standard form of a linear equation that goes through the origin. If the volume is 0, then the time will be 0. So we recognize here, if I write the standard form of the linear equation, we recognize that the time is the dependent variable, the slope is 1 over the velocity times the area, and then independent variable x is the volume. Since if we know how much volume our object has, we'll be able to find out the time. In 3D printing, at least with polymer dispensing, we have cylinders, cylindrical geometry. So the area is the cross-sectional area is the area of a circle. And it's common for these cylinders to have a diameter about 0.5 millimeter. So we can say that this is 0.5 millimeters all square divided by 4. And over here we are finding out the area of the cylinders to be 0.196 millimeters square. It's very important that we keep track of our units. So we have that the time is equal to 1 over VA, the velocity times the area times the volume. And I'm going to rewrite this in the form of the standard equation as we already said. M, which is the slope, times the independent variable. Let us now put into this equation the values that we estimated earlier. T is equal to 1 over, the velocity was 10 millimeters per second. The area was 0.0196 millimeters square. And this is multiplied by the volume. And what we find out is that the slope of this line is equal to 1 over 1.96. And we need to make sure that we keep track of our units. So this will be seconds divided by cubic millimeters times the volume. If the volume of this object, let's say, is 2000 cubic millimeters, which is a cuboid of dimensions 20 times 10 times 10 cubic millimeters, then the time that is required to print this object will be 1 over 1.96 seconds per cubic millimeter times 2000 cubic millimeters, which turns out to be 1020.4 seconds, or 17 minutes. So this analysis shows to us how to evaluate in variable form first the equation, the linear equation that relates the desired or required time to print an object of a given volume if we know the slope. So we could easily say that we can draw the equation here. We can draw the line, and we observe that at time 0, at volume 0, the time is 0, and then there is a linear relationship, with volume being the independent variable and time being the dependent variable. And the slope of this line given by the variable m, which is 1 over 1.96. So this equation can now be used to find the time given the volume of an object to be printed.